is the Hall effect, What is the Hall effect? When a piece of conductor, it may be metal or it may be a semiconductor. Like that here, this is a piece of metal or semiconductor carrying a current. Okay, this is a metal piece, and let that current is made to flow. How? With the help of the battery. So this is the positive pole of the battery, and this is negative pole of the battery. That means current is flowing along this direction. And if the current is flowing along this direction, right, and there is a magnetic field exactly perpendicular, you apply the Fleming's left hand rule. Okay, and listen, if the current is flowing, from this end, which is the left hand side, current is flowing from left hand side to the right hand side. That means electrons are moving from right side to the left side, and magnetic field is acting perpendicular to this metal strip. Then what will happen? Okay, an electric field will be produced inside the conductor in a direction normal to both the current and magnetic field. There are always three axes: x-axis, y-axis, and the z-axis. Let we assume that this axis is x-axis, right, and this axis is z-axis. Then electric field, there will be electric field along the y direction, because current is along x, magnetic field is along z. Then electric field will be along the y. This is y direction. Now if I'm coming the case, if this strip is of metal, right, and strip is of metal, mean electrons are moving from this end to this end, and current is flowing from left to right. Apply the Fleming left hand rule. You know how the Fleming left hand, this is my left hand, so magnetic field, it is along the z direction. Okay, and current, how the current is, actually, as I'm looking the figure, I'm correctly pointing this finger towards the current, right? Now the force will be along the thumb, this thumb, and this thumb is along the y direction. That means a force will be exerted on the electron. So that means the electron will start accumulating at here, and what left behind? The positive charge. So positive charge will be here. So when electrons mean negative charge is accumulating here, positive charge here, so a potential difference develops between these two ends, right? And this potential is called the Hall voltage, because negative charge is there, positive charge. Whenever there is a charge separation, there is a potential difference. That potential difference is called the Hall voltage. So this phase will be negative, this phase will be positive if the electrons are moving then. Okay, this to remember. Now again, if I think that this is a strip of semiconductor, p-type semiconductor, then current is flowing like this. That means holes are moving along this direction. Magnetic field will be along the z. Then there will be force on the holes. Then hole starts accumulating here. Holes mean positive charge. Positive charge starts accumulating here. What left behind? Negative. Again, separation of positive and negative mean establishment of the potential difference. So when the potential difference appears, that is called the Hall effect. So whenever charges they are separated, electric field also develops. Electric field is always positive to negative. So in this case, electric field will be along this side, along this side, which is the y direction, inward y, because this is my x, this is z, then this is y, then inward direction is minus y. So electric field will be established positive to negative, and this is called, and electric field is positive to negative mean y direction, maybe negative y, no problem. Current along the x, magnetic field along the z. So the this electric field which is along the negative y direction, this is called electric field is produced normal to the both the current and magnetic field. Okay, this is called the Hall effect. Okay. Now, what is a Hall effect, right? To explain the Hall effect, we consider a strip, this one, and let us take a strip placed in a magnetic field. This is the magnetic field which is pointing along downward in direction. The field is perpendicular to strip. The magnetic field is perpendicular to the plane of the strip. Okay, the coordinates are x, y, z. So this is the direction of magnetic field. This is the direction of the magnetic field. And the inward magnetic field, if you want to show the magnetic field perpendicular to the plane of your paper, then mark this cross, then mark crosses like this. So these crosses shows that the magnetic field is perpendicular to your plane of the paper, and this is a plane of the strip, which is this one. Okay, now let a current is made to flow along this direction, along the z direction. Current is made to flow along the z direction, right? So current is flowing along the z-axis, and electron will move with velocity Vd. So current is flowing along the z-axis. Current is flowing along the z-axis. If the strip is of metal, then electron will move along the negative z direction, and electron will move with velocity vd. Okay, with velocity vd. Vd is the drift velocity along negative z direction. So because electron, they are moving along negative z axis, so velocity is vd, velocity of the electrons. So here shown, the current is along this side and drift velocity is along this side, drift velocity of the electrons. So the electrons will experience a force by Fleming left-hand rule. And what is the formula for the force exerted by the electron? So this is a vector quantity, force. The Q means the electronic charge, which is minus E, then Vd vector cross the P vector. Remember here, if you take the magnitude of this vector quantity, that becomes Q, Vd and B sine theta. B sine theta. What is theta? The angle between Vd and B. And here it is 90 degree. And sine 90 is 1. So the expression becomes only QVP. And Q is minus E. So this is the expression of the force on the electron in magnitude. So this now I am writing the force in magnitude. Now this is not the cross product, but it is simply the multiplication. Okay. So this force, it is in magnitude. So this is the this is the direction of magnetic field, and electrons are drifting towards negative z axis. So they will experience a force, and force will be along the x-axis. This is very simple if you apply the Fleming's left-hand rule. You can find the force acting because forefinger points the direction of the magnetic field, right? Magnetic field is downward, and current, it is along my side. Okay, this finger, which is I'm wearing a ring, and I'm pointing that finger along my side, and along the thumb, there's the direction of the force. As I'm looking, this direction is along the positive x-axis. So it is along the positive x-axis. The force will be along positive x-axis. As a result of this force, which is in magnitude EVDP, there will be force on the electrons. Now just look here. The electron, because they are drifting along negative z, they experience this force. So they start accumulating towards the right hand side of the strip. So negative charge starts appearing here. Negative charge starts appearing here, and left behind the positive, which will be on the other side of the strip. The negative charge on the right hand side and positive charge on the left hand side. So due to shifting of the positive and negative charges, when the electrons, they are shifted towards negative side, so developing a positive charge on the left hand side. The direction of the electric field, it is always positive to negative. So this set up an electric field. Electric field develops. So electric field mean potential difference because they are related. Potential difference is electric field into the distance, or you can say electric field is potential difference over the distance. Distance mean this distance, which is d. So potential difference becomes E electric field into d. And this potential difference is a voltage, or you may call it a voltage. So negative mean lower potential and positive mean higher potential. So due to the electric field, now as there is a electric field is there, like here electrons, they accumulated here and left behind positive charge. Now what happens? More electrons are coming and they are moving along this side. Okay, so what will happen? The electric field, it is positive to negative. That means electron will experience a force along this direction due to electric field, because electron is negative. So here it is positive and here it is negative. So electron will experience a force along this side. But magnetic force tries to pull the electron along this side. So electron will not move to this side or to this side when the two forces becomes equal. So tendency of the electric field will be to force the electron to move this side, and magnetic field tendency will be to force the electron to move this side. So electron will not, now there will not be more accumulation of the negative and positive charges, because a stage comes when electric force and magnetic force becomes balanced. Okay. So when the two forces becomes balanced, electric force is E into capital E, magnetic force is E into B into Vd, which is the drift velocity. So equating the two, in equilibrium both are equal, right? And there is a relation of current and drift velocity. I is equals to NEAVD. This is a relation between current n drift velocity. Keep in mind, n shows here the number density of the charge carriers. Right? So we are finding, because the forces are equal, from here. The E and E cancels out, and Vd becomes, from this relation, E upon B. So substituting Vd here in this expression, then I becomes NEA E upon B. And we find the value of N from this relation. N becomes, Bi upon, N becomes Bi upon N E A. This is capital E, mean electric field. A is the area. You know which area? Which area here? This is to be noted, the area. This area is, what is this area? This distance is how much? The cross-sectional area has to be taken through which the current is flowing, okay? And this is the cross-sectional area. And this length, this is what? This is the D, okay, from here to here. And this thickness is how much? Small l. Small l is the thickness of the strip. So this becomes the area. Substituting the value of area in this relation. Again, keep in mind, area is the cross-sectional area of the strip through which the current, because current is flowing like this. So this area has to be taken. So L is the thickness, or you can say the height of this strip. So number density is upon substitution of the area. Okay. Now E into D, electric field into distance. This is the Hall voltage. This is the Hall voltage, This is not the velocity. Hall voltage. V, electric field into distance. This is very important. This is the Hall voltage. So if we apply the voltmeter across the strip, like that, like here, then we can find the value of potential difference. Okay, potential difference. And also the Hall effect proves that charge carriers are electron, or the charge carrier are the positives. We can see from same magnetic field and current applying. If we apply again magnetic field and current, again magnetic field negative z direction, like current is also the same. So this is the direction of current. When current is along this side, magnetic field is like this. Again a force will act along the same direction. But if the charge carriers are positive, what will happen? Then the positive charge will start accumulating here and negative charge left behind like this. Because as the current is flowing and current is due to the positive charge, in real practice, the positive charge, they are moving along this direction. So they will experience a force along this side. So positive charge starts accumulating here and left behind the negative charge. So in this case, so positive charge starts accumulating here and negative charge left behind. So thus in this case, so when we measure this potential difference with the help of the voltmeter, now the right hand side is positive. So indirectly the Hall effect tells us that what is the type of the charge carrier which is flowing through any strip. We can differentiate whether the charge flowing it is negative. The Hall effect is also described by means of the Hall coefficient written with RH. And what is the Hall coefficient RH? This is Hall electric field established. Okay, Hall electric field which is established. Okay, EH means Hall electric field per unit magnetic field and per unit current density. So this is called the Hall coefficient. Upon substitution of EH, the Hall coefficient becomes simply -1 over NE, where N is the number density. Okay, number density means charge carriers per unit volume. So this is the expression of the Hall coefficient. And access for you, you tell me what is the importance of the Hall coefficient and what is the mean of this here negative sign. This is an exercise for you. Okay, I'm going to explain the Fleming's left-hand rule, and this is not the Fleming hand, is actually my hand. Okay, now you stretch fingers and the thumb like this. You stretch like this so that angle becomes between thumb and forefinger 90 degree, and between forefinger and middle finger again 90 degree. Okay, so like this angle is again 90. So this angle is also 90. So this forefinger, it will point towards the direction of magnetic field. Okay, so remember, it will point towards field, and then thumb points the direction of force. Thumb will point towards the direction of the force, and this finger will point towards the direction of the current. Okay, and this left hand rule is applied in the case of the motor. In motor, electrical energy is converted into the mechanical energy. So in case of motor, there is magnetic field and current is made to flow through the coil, and then that a force will be exerted, force will be there on the coil which will make a torque, right? Now this is a Fleming left hand rule. Now I'm coming to this is my right hand, and this is again my right hand, and again making 90-degree angle between the forefinger, middle finger, and with the thumb. Okay, now again this is this finger. It will point here again the magnetic field. Now here it is the induced current. Okay, and along the thumb it is the motion. And this Fleming right hand rule is generally applied in case of generator, where the induced current or induced EMF is produced, right? Induced EMF or induced current is produced because of the motion of the coil. So remember now the field, induced current, and the motion. Now look, magnetic field, left hand, right hand, current, but this is here it is current, here it is induced current, here it is force, here it is the motion, right? So what current? Here magnetic field, here force, here motion. So that's Fleming left hand and Fleming right hand rule. Okay.